the buildings, or the fourth one I would say is the building design itself, which is uh, the shape of the building, the more glass concentrated buildings. Previously, how it was, there was a huge chunk. The facade was, an equal mix of the glass and equal mix of
Yeah, the way.
materials.
You'll have to point the ear. Yeah, that is for the up and down.
Yeah.
The next time. Just check if it point here. You should point here.
I should point that.
This, yeah, arrow button. The down one. Is it working?
Not now.
Okay. Let me handle it for you.
I even need it. Okay.
Okay. It's working?
Yeah, I think so. Okay. Yeah. So this is exactly what I was talking about. So by design itself, the buildings will be required to be more modern, right? That's the trend, right? So every architect, a lot of you are architects here. So you also like something which is different, unique, right? It has not been done before. Not like straight line, straight rectangular placement. I need something which is more fluid, which is more modern, right? I will also use different kinds of materials in that, right? And then the last trend that I will speak about is the real-time data and the AI, which everyone knows about it, right? Because it's part and parcel of our life now, right? So everyone will have some smartwatch on their hand, counting their heartbeats, or I don't know, breath analysis, or water reminder, or I don't know. I mean, there are a lot of things, happening. So these are the general trends that is actually affecting or driving the innovations in the building industry. I will not focus on all the 5 aspects, but I will restrict to only one aspect, which is the freeform and dynamic design, because this is more relevant to us right now. So, just to give you a brief, I just want to take you back to the history, okay? Just a quick bit of a story. And the story goes from something good. Yeah, something where the architects and engineers were like this around 40 years ago. You can imagine. This was the action scenario. Here, my professors, they used to tell me, like, in the engineering drawing, I used to have this big, cross ruler, like some 7-8 types of pencils and so on. And this is how the crafting or the basic designing used to be done. It was actually really good, because the touch and feel was there. You used to go to the site and see which material, physically you used to see which material is more effective, right? Which will look good, what is the texture. And now that created, over the period of 40 years, it created a bank of, ideas, right? It came in the textbooks and it got stored, right? Now, talking about the trends in the geometric forms, there are a lot of new design, new ideas. I'm just taking you to think about the design iterations at that time, how it used to be, where how deeply the experiments used to be done, right? Because it was practical, physical. If you want to experiment something, you need to redraw it, right? Nowadays, even in AutoCAD or some other softwares, it is not just Control Z, undo, and you are done. It was not possible there, right? Because it was physical drawing, right? So there was not so much of complexity in the design, right? Because when you are limited with the resources or drawing by your hand, it's just your thought or your skill of visualization that is giving you that advantage of designing a modern building, right? But the trend has changed. You will see that in general now the complex buildings are basically of a couple of kinds. I will speak about all of them. One is the extruder kind. So extruder kind is like you have a floor plan, right? And you basically replicate it floor by floor, and it just goes vertical, right? Urbanization we are talking about, first trend, remember? So that is high rise. Everything on the high rise. So this is the high rise. Couple of buildings here, couple of them are buildings out. Then the second one is the rotor, which is also similar to the extruder, but the floor plan has a similar configuration, okay? But it follows a certain design principle where it tapers, curves, okay? Or, loses its texture somewhere, and then, the different materials are being used at different areas, but more or less, same floor plan. The scaling is different at different floors, okay? So this is a rotor kind of a building. Third one is a twister or tordos. So twister or tordo is basically, you have a floor plan, you extrude it up, and you twist it, turn around, right? So this is another design philosophy of a vertical high-rise building structures. The degree of twist doesn't matter here. It depends on the architect or the thought process, what actually is going on. But in principle, this is the design, how it goes, right? The last one is a freeform, right? So freeform can take any shape, it can have any idea, it can have multiple different floor plans, multiple different design philosophies at every level itself, multifunctional, multi-purpose buildings. This is like a freeform building. So like example, this is a Baku Tower, Twin Tower in Baku. This is one of my favorite buildings because it featured in many of the films that I really like that building. And of course, the one from Dubai. So these buildings, they have a special, application, the design, the fluidic nature that it has. It doesn't follow one single design principle, but have a lot of things, a lot of materials also has gone into it. Of course, up from the outside, it looks like a glass building, but it's a really great, energy efficient building. Okay. So just to give you another generation of development. Okay. So this is what was being followed 40 years ago and then 20 years, and now this is the concept of modularity. Now, so what do you mean by modularity? So now you have to think that I am having a computational backup where I can design something, I can iterate it, I can experiment with it, I can do some analysis, and then I can again come back, do the changes, and follow the same process to make it more efficient. Okay? How it is possible? It is possible because of the computational user architecture now, right? So I started off with multiple floor plans, okay, some random floor plans, right? And then came up with this. You see this? This is a parametric tower exploration by Nikolai, and this basically started from here. And because of the multiple iterations, experiments, analysis can be daylight analysis can be wind analysis can be energy efficiency analysis. I mean, n number of things can be done, can be optimized, and then you have finally something which is there in the MCT in Toronto. You see, every building is different, right? It all started from there. Do you think this was possible 40 years ago? Never. Why it is possible now? It's only possible because of the computational engineering that has gone into it, right? Okay. So now, what is basically this computational engineering? What is this AI? What is this generative, agent-based, and iterative engineering? So this is basically a Python script, simple Python script. Okay, just for that module, right? We went to from here. We went to this. Looks familiar?
Really?
So this is the grasshopper script, which plugs it for the analysis. So design analysis being done in the similar environment. Earlier we used to have tools for two different things: designing separate, analysis separate. Now we have tools where we have the freedom to do the changes then and there, and then do the iterative method, do the necessary change, go back to the design board again, and do the iteration again. This is the result. Okay, this is the third generation. First generation, second generation, third generation. This is the AI in architecture. This is what you are getting now. And this is the AI prompt drafting process, you see. integration of everything in that. This is where the architects are right now. From the previous slide, you remember, and we can get the drawing boards. So this is the journey. This is the 40 years what we are talking about, right? Now, so this was happening globally, right? So this complexity is already here in India, right? At different levels. So this is a tower in Noida. This project is called as Cyberthon. Okay, it's a very linear design building on just 2 sides and very complicated on the other 3 sides. There's a stair hanging on the 36th floor till 42nd floor or something like that. Okay, so the stairs are not done right now, but these 2 buildings are almost in 56th floor. Okay, it's already under construction, and this year it will be done. It's a very unique building that we are doing. And it's a very complex job because the angles, the planes, everything is something which even the architects were they drew it somehow, but they were not able to figure out how it is possible. So that is where they called us and we came into picture and we made it. Yeah. Second one is still under the design stage. The tender is not out. This is the New Delhi railway station. You are seeing the 2 electrical domes. Yes, how it is coming up. Design-wise, it's really fantastic. Really fantastic. How are we going to do this? What is the question? Practically, how it is possible to do it in Britain. And third, this is already executed. Building in Kathmandu. This is a Hilton hotel. Here you will see there are 2 kinds of waves. Concave, convex, both going. Right? Imagination-wise, rendering everything looks fine. How it is possible to do 2 curves like that? But it's already done. It's a super building. So, very important aspect, especially for engineers like me. Architects have the computational horsepower to innovate for the megatrend. They already have it. But engineers, we are still very far behind. So how do we, engineer the real-world systems for these designs? And why I'm talking about both architecture and engineering, because I've seen both the sides. Okay, fairly more on the engineering side, lesser on the architectural side, but I can speak the language, right? So if you have to understand or communicate with someone, you have to speak the same language, right? I cannot speak a Farsi to a Marathi guy, right? I have to speak in Marathi to make him understand. So it is easier for me to communicate with the architects because, I know what to speak. Okay. And it's difficult for you to understand because you cannot speak the engineer's language. Right? But I will make it simple. Don't worry. Okay. So it's very complex. Right? But we will solve it because we have another perspective. So it's a mesh. Of a lot of systems that goes into it. In architecture, it's more like you just draw everything, define the functions of different areas, set the floor plan, you're done. But for us, it's really different because there are so many things that has to go into a system to make it functional, to make it performing, right? To make it performing to a certain specification, right? So we have to work on the structural system, we have to work on the lofting systems, ventilation, bracket, drainage, gasket, connection, fixing, glazing, thermal, sealing, handling, construction, and so on. And they also have a lot of subtopics from a design perspective, from a material perspective. So this is just an overview of what is happening in a glazing system. Okay? Just to give an example, I'll just take 2 case studies. So this is the floor-to-floor height. Okay, so the floor-to-floor height generally is around 3.5 to 4.2 roughly. Okay, and then this is the mass of aluminum consumption for that particular floor height. Right. So this is the band that we are talking about. This is general. So aluminum consumption is around 8.4 to 9.1 kilogram per meter square. Why I'm talking about the weight here although I should not speak about the weight, but it's directly related to the
Structure.
carbon plus the structural. Of course, yeah, you're right. This is a structural slide, but yes, it's directly related to both the aspects. So we have to balance the lesser consumption and make it more efficient by design, right? Then this is the stack height. Stack height versus the aggregate consumption. So stack height is basically the distance between the fulcrum of the stack to the height of where the bracketing is happening. Okay, so this is basically the spandrel area that we are talking about. Okay, so the most efficient stack height is say like 600. Okay, because that's the least consumption, you see. And if you say that I will reduce the beam height, keep on reducing the beam height, it doesn't help because your consumption is going up. On the contrary, if you go on a higher side, so say like in Singapore, there is a regulation of having a standard stack height of 1.5 meter. So they are bound to use 8.5 kg anyway by regulation. However, in India, there is no regulation, right? So it is always better to keep that in mind when we are designing a system that the floor height should be considered optimally, plus the stack height has to be considered optimally, because from an architecture perspective, it doesn't make a big difference, but when you're designing a system, it will have a huge impact there. Then what we do a lot of iterations, multiple designs and so on, right? So every node, this is the FMEA analysis, where every node is analyzed to give that optimal solution. This is just one example. Next. Yeah, so this is the same Cybertherm in Noida. This was a complex area to solve from a load perspective and the structural perspective. So the entire floor for 20 floors we had to model in 3D and do a structural analysis. So this is the 3D structural analysis that we have done for this project. Okay, and then this is the second case study, second example of the complex system, how we have decoded. So I'll just speak about a little on the drainage system, how the drainage is working, where we allow the water. So we have to take the water in the system and take it out. There is no way to, have a perfectly sealed system unless, you have bonded the glass from the outside, which nobody likes, especially the architects. They never like it. So they have to have some kind of a groove, some kind of a open groove kind of a system. And then in that situation, we need to allow the water to come in and somehow take it out through a proper controlled method. So that control is very important. So for different angles where the panels are meeting, there also we have to be sure that when we are allowing the water to come in, it has to be flown out in a controlled manner. Okay. Then what? Then we basically integrate all the systems, okay, or whatever we work, and then we finally give a possible solution to the architect and to the developer, and then we say, oh yeah, done. But what next? They always come back and say,
You on the next slide?
Yeah, this is okay. I mean, whatever complexity you have to solve, it's okay. I mean, what more, right? This can be done. I understand that the engineering in the glazing systems has improved over the period. This is okay, but what next? I want to do something like this. This is what they come up with.
Something.
Okay, straight angles, SR building, tall structure, all this okay. Now I want something which is very fluidic, going like this, bends, curves. Okay, is it possible to do? What do you think? This is a possibility. How? How is possible? Of course, it is, since on the slide it is possible. If it was not possible, I would not have put it there. But yeah, I mean, just to make the ice. I mean, there is something. So that comes with an idea like what if we had a system? I mean, that system is parametric, because it has to be parametric. It has to be versatile.
Yeah.
Right. It has to be aluminium. It has to be light in construction. There has to be freedom of design. I can bend, move, create whatever I want. Then it has to be easily fabricated. right? We don't want to burden on the fabrication. We don't want to burden on the installation. It has to be easily installable. It has to be more on a modular kind system. Then it has to be cost effective, right? So what is it? So this is basically a kind of stick system which actually came from the grid lines of the designer to the geodesic structural shell for the engineers. So the same line, we went back to the principles, the same line diagram, how actually you want it to happen, how actually you want the lines to move, we will follow that. This is the basic principle that we thought of, right? So this is the bridge to shell. This is what we call as G2S. From the grid lines of the designer to the geodesic shells of the engineers. What is it? So this is exactly what it is. So when we basically need the line drawings. We will trace up with our system here, and this is the designing phase. In the modeling stage, what we are doing is we are defining the nodes, okay? And these are the lines. Now it has taken a profile shape, which is structurally stable. I don't need a kind of a substructure, which is basically made of steel, but this structure is self-sufficient to take its own load and transfer the load into the building itself using brackets. I don't need a separate structural mechanism, and from the bracket, the load goes to the mother earth, right? And then the third one is generating, because we need to create all these nodes. So that is the generative principle that we have to follow. So every node is different, okay? Because every line is different, right? Stop. Yeah. Okay. Yeah. So this is how the modeling is done and the generative design is done. This is again transferred to the Autodesk software, where we model each of the nodes, and then eventually each node is being fabricated. So this is done in our factory in the Middle East, Shuku Middle East. So we have a centralized factory for all the projects that we are doing globally. Okay, so this is how it is being done, right? You will understand it more better once I show you some projects that we have executed. Just to take your example, this is Ice Arena in Russia. This is the project which is already executed. This is the executed project picture. Okay, how it was done.
Sorry.
Again, we have to start from the 3 lines, as I said. So we created a 3D line model lines in the generation phase. Okay. Then next. Okay. Yeah. So we assigned whatever material had to go in all those small panels. It can be glass, although it's not small, but here it looks small. Whatever material the architect wanted, the same texture, the same. So somewhere the architect wanted a textile method, somewhere wanted like a glass, tinted glass, and so on. Okay. Then every panel was flattened, right? Every panel was flattened, labeled, and then put down. Laid down in a assembly like this. And then this is the calculation for the nodes, how many nodes it will come, identification of the nodes, and then it went for the fabrication. And that was the project that you saw. So this is how the all the cladding specification, all the glass specification, all the material specifications were flattened and then executed. This is one good example. I recently visited here upon the completion. It's really nice. It's a Budif Mall in Dubai. It's a very old mall, not very old, but yeah, 5 years old mall. So this skylight was not there. So there is a big area which was not utilized. Okay, so the owners thought that, fortunately in Dubai, 2 months you have winter time. They call it winter time and this same. So for them it's winter. So December and January, especially, it's a winter time for them, and all this Dubai festival, everything happens, and there's a lot of tourists which comes there, right? So they wanted to utilize this space more efficiently on the inside by doing some cafe or something which is, which where people can sit outside and have some fun, and you enjoy the nature there, right? So they wanted a canopy which is more or less like a shading element. Okay, they never wanted to cover it or have an enclosure or something like that, but just a canopy, just like a shading element. So this is what we did. They wanted some lighting also effect in the evening, so all those things we incorporated and so on. This is how it looks from the inside. I have a few pictures where people are there, but I'm not supposed to use that, unfortunately. So this is where, this is again a restaurant here and a restaurant. So they extend it on the outside. This is what is happening there. That's how they are utilizing the space there. Okay. This is a glass crust that you see, a couple of weird shapes here. So this is again in Moscow, where we did this. This is an open arena there that you see, but it's completely fluidic. How actually it was designed by the architect. And there is one picture. Yeah. So this is from this side. So here also it is open. Again, it has a lot of lighting functions integrated, and this is completely glass canopy there. Okay, with a couple of folk labels also integrated in. This is from the inside, and this opens into the green area. There is a park, small park, and this is where this entire kids activity and fun activity is organized. You see, there are some solar cells also integrated. Yeah, photovoltaic cells, which actually power the openables and plus the lighting system, and plus the cameras also. It was done through that. Okay.
Legend.
Yeah. So this is a TIA airport again in Russia. Very good project because here the G2S has been used as a facade and a skylight both. Okay. So G2S, since it is paraphyletic, it can be used as a facade. It can be used as a skylight. So there is a continuity that is there, right? You don't have to terminate it anywhere. It can be used as a skywalk also. So that's also possible to do a skywalk. So if you remember the Noida project, the sphere that was shown. So we were actually supposed to do that, but unfortunately, the builders, they already gave that order to a guy who will make it in steel completely. So with that steel, that additional load is also going into that building. Unfortunately, they incorporated that load. So they could have, saved so much on, the construction, because we could have done it much later with aluminum. And now the additional load, that also so high, above 36 floors. So they could have substantially reduced a lot of money just because of this particular design or system, but they couldn't do. Although there is one more project coming in Noida, which also has, again, by the same builder, same steel, the same shape, which we'll be going to execute. So this one.
Sure. Okay.
Yeah. So this is the facade and the skylight, which is from the G2S. Again, very less loading, completely less loading. This is similar to the Bangalore airport. If you see, even Mumbai airport is also like that, but we don't have such big skylights in Mumbai airport. Yeah, so this is also a really good example of a business center in Latvia. This is completely parametric, diamond shape coming in and out with three different stages, three different layers. So the building is popping in, popping out like that. Okay. And this is also done with the same principle, right? So you see, this is how it looks here from a closure view. So this is a facade. There is no skylight in this particular business center. Right. So, yeah. For the most fluid design, this is again a project in Russia which we recently executed. I think this got over in 2023, and this is the most fluidic building we have ever done. This is how it looks from the front, and this is how it looks from the inside. right? So it's quite possible. So even if you draw a line like this, we can do something like this. So that's the challenge that was thrown to us, and we actually executed it. Okay, so this is okay, but what next? What next? So next is mostly about sustainability, right? Because you will take some time to think what next. I will also enjoy that time to think what next and do something for sustainability, right? So just to give you a quick, I will not run it for longer time because we are already over time. Just to give you some rough numbers, although a lot of numbers Venu already gave, but buildings in general are consuming or has consumed 40% of the energy already produced. Okay, so say what, like 100 kilowatt of energy is produced, 40 kilowatt of energy goes into the building. Can be in the embodied form or it's a quarter in the operational form. So this is very important for us to understand. World over, this is an average. 100 units produced, 40 units goes into this, right? Now, in a building, from a more macro level, I'm coming to a micro level. In a building, facades are responsible for 20% of embodied carbon in the building. Okay, so just keep that 100 units globally produced, 40 units went into the building. Out of that 40 units, 20% is going into the facade. Okay, so roughly 8 units, right? 40 units, 20% is 8 units. 8 units of the global energy production, okay? 8 units of the global energy production is going into the facade in the embodied form. Okay. Now, if I break up one step further down into facade, what is happening in facade? You will see that there is a total CO2 consumption happening. Okay, so this is for one unit of facade. You will see what is more important to us is this 37%.
Shall I change?
Yeah, which is basically the aluminum profile, and 41%, 9% is the glass, and 41% is the aluminum sheet. Aluminum sheet is basically the ACP, because that's a very common facade element. I would say after glass, the most common is the glass. The second one is the ACP. But ACP also takes a lot of energy consumptions. Now you see this 37%. This 37% is basically of that 8 units. Okay, so roughly it will come around 3 units. Okay, so 3 units of the global energy consumption is going into this aluminum profiles. Now you think the scale. Now you think how much we can save on carbon footprint just by targeting this aluminum, right? This is just to give you some rough numbers where we start, and you can just compare the same with glass, and I will leave it to my friends in the glass industry to take care of that. I will take care of the other part. So we need to understand this whole life carbon. Okay, it's really important to understand this. There are different stages. So stage A1 to A5 is basically till construction, from mining of aluminium till construction. Okay, then comes the operational part, because once it's constructed, people will go get into it and they will start living it, and then the operational carbon starts to come into picture, right? For that, we have stage from B1 to B7. Then once the life of the building is over, roughly what is the life of the building? How much do you think a building is designed for?
50 years. 50 years.
50 years? 70 years? Okay. Yeah. 50 years is a good guess. Anything between 40 to 50 is a good number for the current buildings. So once that building has reached that stage, we have to think about the demolition part, right? So the demolition phase is from C1 to C4, right? And then comes the recycling, reuse, okay, reproduce. From there we get the credits. So basically, when this is how it is classified: cradle to gate, so A1 to A3, cradle to practical completion of front, that is basically, past the factory. This is export, so there is a transportation also involved. And then cradle to grave, which is basically till end of C4 phase, and then cradle is the entire circular activity, right? So this is how the whole life carbon of a building can be understood. Okay. So now you see the first A1 to A4, which is basically from fabrication or in fact mining to construction. It's increasingly important because this is the real embodied carbon, right? From that curve, if you see, 3/4 were embodied and only 1/4 was operational. So this also remains important, but majority of the energy consumption is happening in this phase, right? And what we should do here is to use, low carbon material. We have to do a better design. We should focus on the transportation, the construction itself. The technology of construction has to improve. The site has to be near, so that you don't have to spend something on, more on the transportation. We don't have to really import, make everything local and so on, right? So the sourcing strategy has to be like that. Then in operation, product lifetime, service renovation, all those aspects are there. And along with that, you need to have a good insulation, ventilation, air, PV, and so on, which actually, helps in the building itself to reduce the energy consumption, increase the efficiency of the building. Okay. And then in the last is the reuse and recycling. But today we will speak and see only about that low carbon emissive materials, and the design aspect, of course. Right. Okay. So for this, we have a strategy in Shupo, and we call it a carbon control, which is basically a toolkit, okay, which is basically designed for minimizing carbon in construction. There is a small video I would like to play.
Yes. There's a separate file for it.
You can just skip here.
We can't see it, smell it, or touch it, but it's changing our world, and it's a game changer for the construction sector. Carbon dioxide. New requirements and regulations are posing a major challenge for our entire industry. How can we minimize the carbon footprint of buildings? Our answer is a holistic approach. Shugo Carbon Control makes the decarbonization of the building envelope manageable. Our modular concept enables project-specific CO2 minimization in each phase of a building's construction. Designed to decarb, because safeguarding the future already starts at the drawing board by simply pressing a button to get a full carbon footprint calculation, while certified EPDs serve as a planning guide. We ensure the optimized use of materials, not to mention the individual consultations our CO2 experts provide to turn your plans into a climate-neutral reality. Built to decarb. We accompany our partners on the way to a decarbonized construction industry with future-proof solutions and CO2-reduced materials. For example, with low carbon and ultra-low carbon aluminum or hybrid systems, able to reduce the embodied carbons when you're building envelope. Operate to decarb for building operations that are eco-friendly and economical. Because in the future, operating buildings means operating in a climate-neutral way with products that actively minimize CO2 with high thermal insulation, energy efficient, and smart, with integrated photovoltaics that even turn your buildings into energy suppliers, and with solutions that extend the life of your building through maintenance, repairs, and modernizations. Recycle to decarb. When a building's life cycle ends, a new one begins. Buildings with features of layers of raw materials, our IOF, intuitive facades, digitalizes the building envelope and supplies crucial information about the recyclability of its materials. Light hours will define printing real products and recycling solutions, make it possible to create a closing raw material loop, including construction and tape action. Expensive our ingredients to lies in the smallest particles. Together with our partners, we actively shape the climate-neutral future of construction. CO2 footprint. Maximum control. Triple carbon control.
Correct.
Correct?
Yeah. Biggest challenge with the smallest particle. That's the reality. Okay, so this is basically that toolkit which you just saw, designed to decoup, build to decoup, operate to decoup, and recycle to decoup. So at every stage, we make sure that we are helping out the customer, the builder, the architect, the investor, everyone, consultants, with the right choices at the right time. Because if we miss that thing, then it's too late. Then we are contributing more to the energy crisis. Right? So everything is linked. So at every stage, design stage, build stage, how to manage during the construction time, how to operate. There are multiple solutions for passive ventilation, which actually reduces the cooling load, or even in Europe, it's the heating load, just the opposite. Okay, but the thing remains the same. So we make sure that at every stage we are contributing towards this decarbonization. And of course, at the recycle to decoup. So this is really interesting that we have now achieved almost 18% reduction in CO2 consumption just from the aluminium part. And we are also able to recycle the most important insulating material, which is PA 6.6, up to 90% recyclability. And that is helping us to reduce another 2.5% on the carbon footprint side. Okay. Right. So, yeah, next slide. So, just to give you a brief on the design aspect, how we are going to do it. I'm just little deep dive into the only one topic on the design aspect. I'll just leave out the operate, build, and recycle part. Just deep dive into the design aspect. How we are helping to decoup from a design perspective. So there are certain values that you have to keep in mind, which will help in making the building better, right? From a design perspective, how we can make sure that the building is performing better, right? These are the most important three aspects. It is also identified by LETI. LETI is, again, Energy Institute in London, and they have taken up the task of being net zero by 2050. In fact, 45 is the first target. Eventually, they will end up in 2050. For us, it is 2070 to be net zero. Okay. So how are we going to do it? We have already started in Shuko pushing this design to decoup since end of 2022. So we have already started doing it in our projects. So how do we do it? Okay. Sorry. Yeah. So this is one project in Ahmedabad. It's the Adani Energy House. The intent that was told to me was, I want to reduce the operational carbon. I want to reduce the space cooling demand. I want a balanced daylight. I want, the running cost of the building should be less. I want to reduce the thermal breaking. So this was the problem statement put across in one of the meeting. And then they were like, I asked them, what is the target value you want to achieve? Okay. What is there in your mind? How much you want to save? Because you have to tell me a number. If you both tell me a number, I won't be able to help you out, with the full trust. So then they said, okay, fine. U value, let us do one thing. We will design value was 1.9 watt per meter square Kelvin. Now, just to give you an understanding where we are. So the industry is at 2.5. At every 0.1 reduction in U value is a massive task. Massive task in the sense, from a design perspective, not so massive, but from a cost perspective, it is massive. Because your glass specification, if it is changing, it will cost you a bomb. Your material specification is changing, again, it will cost you a bomb. Right? So this is where the industry is, industry standard. The industry stretch is 2.1. And anything below 2 is like not imaginable right now here in India. Okay? But I'm talking about the entire facade, entire building. It's not just one window I'm talking about, right? It's the entire facade, you know. So what we did, we went to the functional area design. As I said, every complexity has to be broken down into certain substructures, and then we attack there, one by one, step by step, right? So for this, what we did, in the functional area, I will show you in the next slide what we mean by a functional area. There there are only two things. One is the geometry, how you design that particular profile, and what material do you select. Okay, only two things. So when you work on the geometry, you do a lot of iterations. You play with the shape of the profile, how it should be looking like, and how the different materials are going to integrate into that. Right? With this approach, we were able to achieve 1.87 watt per meter square Kelvin at the same price. That is most important. So from 2.5, we came down to 1.87 at the same price. How it was possible? Again, the same thing. We went with a better material, although it had to be sourced from Dubai. That's a different thing. Carbon footprint was there, but eventually the overall U value is going down because of it. And of course, we worked on the geometry for it. Right? Next slide. Yeah, so this is typically U value calculation of a facade. This is how it actually looks like. This is in the plan B. You will see this is the functional zone. This is what we call as functional zone. Okay. So this is the glass line. This is the glass DGU. And all the heat exchange thermal bridging is happening here. Right? So we just need to focus here in this situation. If I come to a standard area with an openable, I just need to focus here. Yeah. Right? So all the work, material change, design, geometry, everything happens here. There were a lot of fins. So again, this is the thermal bridging happening. So this fin is also, getting inside. So it gave a path for the heat to flow in, right? So we just need to focus here and understand, right? So this is the minute detail analysis that has to be done. If any correction, if I'm not able to hit any value, I need to go back to the design again, change the material, or maybe change the design, come back and do this analysis again. This model it usually takes 7 to 8 hours to give you the result. The software, okay, and it's one of the best softwares in the world. It's called Fixo for the U value calculation, and it takes time, but it will give you genuine results, most accurate results it will give you. So if you go for a practical check in a lab also, it will be similar. So the simulation, it takes time, but it's worth, right? Okay, so this is how the first topic, U value, have to be included at any point of time when you are designing for decarbonization. Okay. Second thing, most important, air tightness. This is directly proportional to the heating load or the cooling load of a building. Okay. If you are able to control the air ingress, half of the problem is solved. You are solving the acoustic problem, you are solving the heat load or a cooling load problem, you are solving the dust problem, you are solving the whistling noise and so on. Many things, okay? But again, the intent, this is Fairbox Noida, another beautiful project in Noida. DFI was the architect and Avante is the consultants. Here, the same problem, operational carbon has to be reduced, space cooling demand has to be reduced, acoustic should be good, HVAC malfunctioning has to be, okay? Now, again, the same question I asked them, what is the value that you want? You have to tell me a value. Then, after understanding, after speaking to their HVAC experts, and then so on, they came up with the value of less than 3 meter cube per hour per meter square. Okay. Now you see where the industry is. It's 9 times more. It's at 27. And they want to be the best in class. If we stretch also by doing some modifications, we'll be at 9. Right? But the requirement is less than 3. And do you think they will pay the cost for this? They will not. Okay. So, same principle. you need to decode, get it to one specific value, see what is the design that is required to be done. So this is basically air exchange is happening on the interface areas, where the interfaces are, where there are different materials, different panels, different structures. Wherever the interface is there, you will have air leakage, right? Simple common sense logic. So we went there. When we went there, we saw again the same thing. Either we have to play with the geometry or we have to play with the material. Simple, very simple. Now, in geometry, what we did, we decided to work with multiple barriers, right? In a facade system, it usually starts with a 2-barrier system, maximum goes to 3-barrier system. You can further have 4-barrier system, 5-barrier system, and it can be endless. But there is a repercussion on it. Since Noida is a seismic area, if the system is too tight, the facade will not move, and if an earthquake comes, the whole building, the glass will shatter, right? We need to allow the movement. So there has to be some restriction there, right? So then we thought, okay, fine, we worked on it, and we finally hit at a 600 test pressure, a value of 3. Okay, which is class 4 in as per EA. This is basically for windows and doors, and they wanted the same values, performance values for a facade system. This is how it was, complicated. Every interface, so this is on this interface that you see. So this is the first barrier, second barrier, third barrier. This is how it is. First barrier, second barrier, third barrier. So this is our interface area. This is where 2 panels are getting joined, right? Then there are situations where you have SIG also, then how to deal in such situation and so on. So different designs for different angles, and we were able to solve it at the same price. Okay. Sorry,
yeah.
Yeah. So third topic last when it comes to design to decarb is the material consumption itself. Okay. So how do we optimize to reduce material consumption? This is one classic example in Hyderabad. The building is called as Yam Nazami. It's almost done. Panchip from Pune are the architects, and facade consultant Alsam Design was there, but they later got changed. Here again, the problem statement was, I need to reduce the embodied carbon, and this is a real case I'm telling it. I want to reduce the dead weight on the structure. Improve structural performance. I need improved structural performance, and I need to reduce the material utilization. So it was a bare minimum, because we were told that we don't have to cross a certain kilogram consumption of aluminium in that particular project. God knows why. I don't know, but they were very clear. I need this. I never had to go and ask them, what is your target value? They upfront told me that, boss, this is the problem, and I need to finish the building in this particular budget, and this is what you'll be giving only for the facade part. Very clear, no problem. So wind load was roughly less, just like Bangalore 1.2, so where it was 1.8. So if you go back to the graph which I was showing earlier, if you derive, mostly you will end up at 8 kgs. If you stretch, you will be like 7.5. Okay. But what they wanted, I cannot disclose you right now, was way less than 7.5. Okay. Okay. So next, right, what we have to do. So here there was very interesting gentleman, Dr. Boha, who is a very literate person in the structural engineering fraternity, and he's an expert in the seismic design. So he helped me a lot, and he was also part of this project to develop a profile system. And even the test lab guys, they were amazed when we did the testing, because it was not designed to take so much of load, but it overperformed. Okay. And it was, again, same principle. We went back to the structural design, we played with the geometry, we played with the load sharing. Of course, material remains the same at the beginning. We can't do anything. We can't change the alloy. So the load sharing, how the load sharing is happening. So how the load distribution has to happen. So we worked on that aspect. Of course, we had to use some FES softwares to optimize the design. I will show you that. And then the load sharing. So we had to play with some kind of principles, standards. Structural design is very complicated. So we have to follow the IS code. It's mandate to follow the IS code. So we had to, somehow break rules here and there, but for good, not just to reduce the cost. That was of course the goal, but not the last agenda, right? And then when we did, we were able to reduce by 25%. So you can roughly calculate 8 ka 25 kitna hoga, we were at that position. Okay, so I was asked not to disclose, but I can disclose this. Rest you can calculate. Okay. So this is how this optimization works. So basically, this is the profile section. Okay, and every profile section has different nodes and different thicknesses, wall thicknesses. We play with the entire geometry, and this is the iteration that is happening. So this is the original design. It's iterating. It will do iterations until it reaches a target value or the best possible value. This will run for maybe an hour, 2 hours. It will reiterate. It's a proprietary software of Shuko. It's called Shuko VLC. And we then come to this point where 95% or 94% of the original weight and 140% of original strength. So with a lesser weight, we are getting more strength. So this is how we were able to do it. Okay. Now, this is again the third topic of design to recap. So there are other aspects, which is really important during the design phase, where we should be very vigilant. Especially when Minu was also talking about, if you don't think about making the building green in the first phase, then you are too late, right? So what should be the orientation of the building? Whether, west-facing facade or south-facing facade, obviously will attract more heat. What can be done? So similarly, I mean, the shape of the building itself is more important, right? So the shape of the building, like form factor, right? The smaller, the lesser the form factor, the better it is, right? Then if you are going with wider elements, don't go with, aluminum spacing at 1 meter, 1 meter, 1 meter. Obviously your consumption of aluminum will go up. Go with a bigger size, go with 3 meters. So you have automatically cut down to vertical, aluminum interfaces plus glass processing also you cut down. You're going with the bigger glass. Go big. Okay, that will reduce. And the problem is people, they don't have solution for big, but it's not so. There are solutions for big, really big. 6 meters cross 3 meters is not big anymore, right? Then choose the right system, consult the right people, select the right material, select the right system. That itself will solve most of the problem. And then in the last, optimize the material. Use, this is standard aluminum 4.9 kg carbon consumption. Then low aluminum and then ultra low. So this is the value. Of course, I mean, we are coming up with ULC and LC here in India also. Sooner or later, we are actually in talks, and maybe by this year, and we will have EPDs also available for us. Okay. This is okay, right? Which question is what next, right? So, abhi ke liye, I will leave it here, and I will leave it for better. You have the questions, and we'll meet again to see what are the next challenges. So, what we saw was a very small part of a very big, chain, right? There are so many things to be spoken about, so many things to be discussed, so many things to be seen, and so I will leave it here and leave it for better. Thank you for being so patient. If you have any questions, I'm more than happy to take those questions. You can.
Amazing.